Hello everyone, it's Jeremy from AI Expedition, and I hope you're all doing well. In this video, I'll show you how you can use TensorFlow records and dataset pipelines to speed up your training code. Saving and loading TensorFlow records can seem a little difficult at first, but once you get the hang of it, it's not so bad. If you've never worked with TensorFlow records or dataset pipelines before, don't worry, I'll walk you through it step by step. The main use case where TFRecords can give you a major speed boost is when you have a dataset that's too big to fit into memory. These days, datasets can be hundreds of gigs big, which means they just won't fit into the RAM of most computers. One way of getting around this is to use batching when you load the training data from your hard drive into memory. I'll show you a naive implementation of this, and I'll also show you another way of doing this using TensorFlow records. As an example project, I'll say that we're trying to build an image classification model for a modified version of the Caltech 256 dataset. This modified dataset contains 256 classes with around 100 images of each class, where each image is 256 by 256 pixels. In the outer directory, there's a label file containing the folder name, image name, and label of each image. We'll use these labels to load our data in the same order for our different implementations. Cropping the images and creating this label file was just something I did for the purpose of this video. But if you'd like, you can find the original version of this dataset by following the link in the video description. I'll take this opportunity to say thanks to the creators of the original dataset, so if you're one of those creators, then thank you. Now, moving on to the code. I've headed over to my GitHub repo for this video, also linked in the video description, and I'll illustrate the training speedup on Google Colab so that you can follow along and replicate this on your side. But you should also see training speedups if you use TensorFlow records locally. So the first thing I'll do is find this title 1 naive training, and under there, click on this button that says open in Colab. That will open up this notebook. This is the naive batching implementation without using TFRecords. I'll go through this file so that you have an understanding of the code, and we'll also see the training speed so that we can compare it to the code when we do use TensorFlow records. Before you do anything, make sure that your runtime is using a GPU, otherwise training will take super long. So you click here, runtime, change runtime type, and make sure that it says GPU over there. Back to the code, you'll see some imports at the top of this file. The first 3 imports are all for building TensorFlow models. We'll make use of NumPy arrays to hold our data before we send that data into our model for training. We've got pill for loading in our images, and we've got time so that we can see how long the code takes to run. So I'll go ahead and run that, and I'll say run anyways, and then I'll run this line to print out the type of GPU that's been assigned to us by Colab, because sometimes Colab might assign us a different GPU. But to make things a fair comparison, we have to use the same GPU in both of our implementations. So you can see here that I've got a K80. Now the next step is to gather and prepare the dataset. This gdown line will download a zip file that contains the modified Caltech dataset that you saw earlier. So that downloaded a zip file, and then I'll run this to extract the zip file. And now I've got the same files and folder structure that you saw earlier. I'll go ahead and split my data into training, validation, and testing sets. And to implement this, I'll create 2 lists, one that holds the image paths and another that holds the labels associated with those image paths. I'll populate those lists by using the shuffled labels file that we saw earlier. I'm going to use a train, validation, and testing split of 60-20-20, so I just calculate the number of training and validation images, and I'll select appropriately from the paths list and the labels list for each of my datasets. So the training set will take all the way up to the number of training images, the validation set will take from the number of training images up until the number of training images plus the number of validation images, and then the testing sets will take from the number of training images plus number of validation images onwards. Now it's important to note here that each of these datasets is just storing the image paths and not the actual images. And this is because we're assuming that our training dataset is too large to fit into memory all at once. I've gone ahead and run this, and then next we'll prepare some data for our model. I could have left the image sizes as 256 by 256 and just shoved them into a model, but I wanted to show you something a little more advanced, and that's data augmentation by using random crops. If you're not familiar with this concept, then basically what you do is that for each training iteration, you would take a random crop from each of your training images and send those into the network instead of the full image. The idea is that a slightly off-centered image of a dog should still be an image of a dog. So this technique just helps to add more training data to your network, and this should help reduce overfitting. Now, since the validation images are still 256 by 256, we have to crop those as well. But we don't just crop them randomly. Ideally, we want the validation and testing sets to be the same on every epoch so that we're not measuring our network accuracy against a moving target. So that's what I'm doing over here. I'm just defining the image size and a crop size, and I'm creating a list containing the cropped validation images. Note here that I'm loading in all of the validation images into memory at once. I'm doing this just for convenience. I'll show you how you can batch the training images, and you can copy that approach for the validation sets as well. But just for simplicity, I've decided to load in all of the validation images at once instead of batching them. And once I've loaded those images, I simply take the center crop of 224 by 224 from each of the images. And with that, we prepared most of our data, and we're ready to build and train a model. I'm just going to use a standard model for this video because the focus is on TensorFlow records and not on building the most powerful state-of-the-art models. So I define an input to the model as a tensor that has shape crop size by 3, which will match the shape of our cropped images. I'm using a pre-trained ResNet 50 model, chopping off the last layer and freezing the parameters of the network. Then I add a global average pooling layer, some dropout, and a dense layer with the same number of nodes as the number of classes in our dataset. We're using an Atom optimizer and sparse categorical cross-entropy. I know I've gone through the model building quite quickly, but this is all standard stuff, and the focus of this video is on training speed and not model building. But if you're interested in learning more about this, please check out my website, aiexpedition.com. Back to our code, this gives us a function that can build a model. So I'll go ahead and run that, and now we're ready to train our model by batching our training data. So we call our function to build the model, declare a batch size, and I'm taking the starting time so that I can measure the total time it takes to train this model. Then I've just set this up so that we train for 10 epochs, and I also want to time how long each epoch takes. This next for loop is where the batching and training happens. I create a start index, which should start from 0 and not exceed the number of training images, and it should be incremented in steps of the batch size. The end index is just the start index plus the batch size. Then we extract the batch of image paths and their labels, and load in the batch of images. We convert the list of images to a NumPy array so that we can send them to our model, and then just call the model fit function for the batch of images and the associated labels. And I've just realized that we don't actually need this batch size parameter in here, so I'll go ahead and remove that. So when you open this code in Colab, you probably won't see that. Once we've completed training each epoch, we can call the model evaluate method to check the validation accuracy, and then get the time again to calculate how long the epoch took. Once all of the epochs have run, I print out the final time taken. You can also load in the testing set and check the testing accuracy if you'd like, but for simplicity, I've just omitted it. I'll go ahead and run this, and it's going to take a while, so I'll come back when it's done. Alright, I'm back, and you can see that it's taking around 200 seconds in epoch, and in total it took around 2070 seconds. The first epoch just took a little longer because of setup costs, and after training for 10 epochs, we've got around 70% accuracy. So that's the completely naive way of training in batches when the dataset is too big to fit into memory. I'll just free up these Colab resources by closing this session. So I'll say manage sessions, and then I'll say terminate. Now let's learn about TensorFlow records and pipelines, and let's see how much we can speed up our training. I'll head back to our GitHub repo, and under the heading 2 using TFRecords, you can go ahead and click this button, and it will open up this file in Colab. This file starts almost exactly the same way as the previous file, but I've added some extra imports that we'll use when creating our TensorFlow records. I'll go ahead and run these imports. I'll say run anyway, and I'll run this code to check the GPU. You can see that we're still using the same GPU as before, that's the K80, so that when we compare the training time in this notebook, it will be a fair comparison. Next, we download the dataset just as before, so I'll go ahead and run this, and run the code to unzip the zip file. The difference from the previous file comes in here, because now we're going to create a TensorFlow record to store our data. This code block here is still the same. It's just populating these two lists, which contain the image paths and the associated labels. We're going to use those two lists to create a TensorFlow record containing our data. So I'll go ahead and run that. And now you may be wondering, what exactly is a TensorFlow record? Well, a TensorFlow record stores your data in a binary file format, and that's useful because it takes up less space and can be read more efficiently. Using a TensorFlow record file with dataset pipelines will help us to speed up our training code. We can create a TensorFlow record file using a TensorFlow record writer. So I do that in this line, and this means I'm going to save my data in a file called caltech.dataset.TFRecords, and my TFRecord writer variable will just be called writer. Using this writer, we can save our images and the associated labels to the file. So I loop through the list of image paths and image labels, but I'd like to store the actual images and not just the paths to the images. So this next line here just reads in the image. And what I'm doing next needs a bit of explanation. To allow the TensorFlow record writer to save our image and label, we need to create a tf.train.Example object. This is just an object with a single attribute called features, and this features attribute is just a mapping containing feature names mapped to feature objects. A feature object has three attributes: bytes list, float list, and int64 list. And you can see the different data types that you can associate with each of these. I'll leave links to this documentation in the video description, but maybe this will be clearer to you once you've seen an example. So back to our code, what we'd like to do is create feature objects for our image and label. The label is pretty easy. We just store it inside of an int64 list. So here, you'll see that I'm creating a variable called class feature, which is a tf.train.Feature, where the int64 list attribute is equal to tf.train.In64 list, where the value is equal to this label inside of a list. So that's the label, and it's pretty straightforward. But now we need to make a decision on how we store the image. One way we could do this is to get the pixel values of the image and store them as an int64 list. But that's not the most optimal way to store an image, and here's why. An int64 variable takes up 8 bytes, so we're going to use 8 bytes per pixel. Our images are 256 by 256 by 3, and we have 256 classes, with around 100 images each. So to store that would require this many bytes. We can divide that by 1024 to get the number of kilobytes, and again to get the number of megabytes, and again to get the number of gigabytes. And you see that this would take around 37.5 gigs. In contrast, you can see up here that our dataset is only 287 megabytes. And that's because for the dataset that we downloaded, each image is stored in JPEG format. So it takes up a lot less space to store our images in JPEG format, and the features type that can handle that best is the bytes feature type. So that's why in these lines over here, I'm creating a bytes buffer and store the JPEG formatted image into the buffer. Then I extract the bytes value and I store it in the bytes list attribute in another feature. Note here again that this image bytes is surrounded by a square brackets because this bytes list attribute needs to be a list, and this image bytes variable is just a single bytes variable. Now we can take our bytes feature and our class feature and stick them into a mapping to create a training example. And we save that training example to our file using our writer. So we repeat this process for every image and label, and that's how we create a TensorFlow record file. I know this seems quite complicated, but if you're working with a large dataset, then the speed up you get should be well worth this effort. I'll go ahead and run this, and this will take a while to generate the TensorFlow record file because it has to read in all of the images and put them into this file. So I'll go ahead and pause here and come back when it's done. Alright, now it's created the TFRecord file. You can see it if we click on this button, and you'll see it over there, 274 megs. I'll go ahead and close that, I'll mention here that creating this TFRecord file is something that you would probably do in another script as part of your data preparation. You wouldn't really make it part of the training script because you don't want to have to generate this file every time that you train. I'm just putting it here for this video so that it's easier to follow the code. Now, once we have this file, we need to be able to read data from it. We need to tell TensorFlow how to pass the data into TensorFlow variables. So these lines over here specify a mapping from a feature name to a TensorFlow variable type. So here image will map to tf.string, and this first parameter over here, which is this open close square brackets, specifies the shape of the variable. Since this is an empty square bracket, it means that we're expecting a single value. The class is also a single value, and it maps to an int64. You would think that TensorFlow would automatically be able to figure out our data types, since we already specified a similar mapping earlier over here. But that's not how it works, since these feature lists over here could map to multiple data types. So that's why we need this mapping. This next function will be used to specify that TensorFlow should use this mapping to pass our data. This bytestrings to pixels function will convert the byte string stored in the image key into pixel values. So you see here that we decode the image and then reshape it. Then we return the decoded image and the label. I'll go ahead and run that. And then this next function ties everything together. It takes in a file path to the TensorFlow record, and it creates a TensorFlow dataset object based on that file path. On that dataset, we apply a mapping to every example in the dataset. We tell TensorFlow how to parse the example using the parseData function that we defined over here, and then the results from that mapping will be passed into the next mapping, bytestring to pixels. So after this point, for every example, we'll have two values, the image and the class. This parameter over here, numParallelCalls is equal to autotune, allows us to process multiple examples in parallel, and this gives us a bit of a speed boost. So I'll run this function, and then I'll call this function to create our dataset. Now it's important to note here that even after calling this method, we haven't actually loaded any images into memory. This is because the data is loaded in a lazy fashion for optimization purposes. So until I actually use a value from this dataset, nothing gets loaded into memory. Let's take a look at what this dataset looks like if I print it. I'll just add a code block, and then I'll say print Caltech dataset. It just says that this is the parallel map dataset, and it gives us this shapes tuple and this types tuple. This lets us know that each element in our dataset contains two values. The one is our image that has shape 256 by 256 by 3, and the other is our label, which is just a single integer value. We can get access to the first element of this dataset by using the take method. So I can say Caltech dataset.take1. If you're interested, you can see a list of available methods on the dataset class at this URL, which I'll link in the video description. For now, let's take a look at the take method. It says create a dataset with at most count elements from this dataset. So calling this take method and passing 1 creates a new dataset that only contains the first element from the Caltech dataset. That element still isn't loaded into memory, but now we can load the element by iterating through the dataset. So I can say for image, label in Caltech dataset.take1, prints image is image and label is label. I'll go ahead and run that. And you can see that our image is this tensor, and that tensor has shape 256 by 256 by 3. And our label is another tensor with a single value of 224. Another thing to note is that this take function doesn't move on to the next element of the Caltech dataset if we call it again. It will just keep taking the first element of the Caltech dataset no matter how many times I run it. So if I keep running this, I'll keep getting the same tensor with the same value 224 over here. I can also pass a bigger number to this take function, so instead I can say take 3 and then run this, and it will give me the first 3 elements in the dataset. So over here, that's the first element again. Again, it's got this 224 value, and the second training example that has a value of 80 in the label, and then the last example, which has a value of 196. So now you know how this take method works, and I'm going to use it to split the Caltech dataset into train, validation, and testing sets. So I perform the same calculation that I had in the previous script to calculate the number of training and validation images. And I can say that for the training dataset, we only want to take examples up to num_train images. So that's easy, we already know how to use the take method. And then for the validation dataset, we can use the skip method to ignore that many examples, and then use the take method to get the validation images. So it's Caltech dataset.skip the number of training examples, and then just take the number of validation images. So I can go ahead and run that. And then for the testing dataset, we can just skip all of the training and validation images and keep the rest. So that's what we do over here with the skip function. Just a note here again, that defining the datasets at this point doesn't actually load any of the images into memory. The images will only be loaded into memory when they're used. So that takes care of splitting our dataset. Now remember that the images in these datasets all have size 256 by 256, but we're going to train a model which takes in input images of shape 224 by 224. So here I define the image size and the crop size. And we're going to do the same data augmentation that we did before. So for every training iteration, I'd like to get a random crop from each image. So here I define a mapping method that I'll use on the training dataset that will take random crops from the training images. You might be wondering why this method takes in 2 parameters, whereas our previous mapping methods only take in 1 parameter. And the answer to that is because if you look at this byte string to pixels method, it returns 2 values. So those values are the image and the label, and that's the last mapping that we apply to our datasets. So those 2 values will be passed into this data augmentation method. So I'll go ahead and run that, and here I'm defining that the augmented train dataset is created by calling this mapping on the train dataset. Then from the last notebook, you'll remember that the validation dataset always uses the center crop of each image, and that's done to remove the randomness while evaluating our models. So we do the same thing here, but by using TensorFlow datasets. This test data preprocess method is similar to the train preprocess method, but it doesn't use random croppings. Instead, it takes the central crop of each image. So I'll go ahead and run that. And with that step, our data is prepared and ready, and we can build and train our model. This is the exact same function we had before to build our model. I'll go ahead and run that. Then in this code block, I call the function to create the model, declare the batch size, and get the time. Then I create a loop to train for 10 iterations. Now this inner for loop here loops through this training dataset in batches. I'll just illustrate up here. With this piece of code here, I'm iterating through the values of this train preprocessed augmented dataset in batches of 128, and I've just added this take 1 over here so that I only go through the first batch. This batch function over here just groups consecutive elements in a dataset into batches. I'll go ahead and print this so that you can see what this looks like. You can see that the image variable is this tensor, and that tensor has shape 128 by 224 by 224 by 3. So it's a batch of images. And then the label batch variable is a vector of size 128. So back to our training code, we're going through every batch, and note here that I don't have this take 1 at the end, so it is going through all the batches, and then we're taking each batch and passing it to the fit function. After we've completed training, we again evaluate the model on the validation dataset. So now that we're using TensorFlow records, let's train and see how much faster it is. I'll go ahead and run this code and come back when it's done. Alright, I'm back. This time it took around 1,700 seconds to train, also getting to a validation accuracy of around 70%. So it took around 300 seconds less to train while maintaining a similar accuracy. But we're not done yet. We can actually shorten the previous code block. For starters, we don't have to loop through the dataset like this. We can actually just pass the batched dataset into the fit function as follows. We say model.fit, and then we pass in the train dataset .batch with the batch size, and we say validation data is equal to validation processed .batch with that batch size. And note here that I've got epochs is equal to 10. I'll go ahead and give this a run and then come back when it's done. Alright, it's done. And now you can see that it only takes around 1280 seconds while maintaining around 70% accuracy. That's around 2 times faster than our previous notebook where we didn't use TensorFlow records. So hopefully you can see the benefits of using this method. If you would have trained for 2 hours, you now only have to train for 1 hour, so you've saved yourself an hour. Also, sometimes you may want to try out many models on the same dataset, so setting up your dataset like this will save you time on each of those runs. Obviously, the results may vary across different projects, but I'm still expecting you to get a decent speed up in your own projects. I hope you enjoyed this video and learned a lot from it, and I hope you'll apply these techniques in your own projects. If you enjoyed this video, please like it and hit the subscribe button to stay updated with my latest content. You can also check out my website, aiexpedition.com, to learn more about AI.